So we will first solve this balanced reinforcement ratio. Balanced reinforcement ratio. Okay. So we will take the same section that what we have considered. Okay. Which is basically your let's say I'm taking this section. So which we have taken this cross section. Okay. And instead of this, I'm going to take a AST. I'm going to calculate this AST, which is going to give me a balanced reinforcement condition. Okay. So what is the strain that we are going to do for a balanced condition? We have discussed that. What would be the condition for balanced failure? The concrete at top is going to reach a strain of compressive strain of 0.0035, and what would be the strain on the tension side? That is going to be here, which is basically going to be yield. So for Fe 500, Fy is equal to 500 megapascal, right? So epsilon y is nothing but 500 divided by 200 into 10 to the power of 3, which works out to be 0.0025. Okay, so this value is going to be 0.00, 0.00, so is going to be 0.0025. Okay, so this is a balance condition. So what is the balance condition? Concrete at top reaches its failure strain of 0.0035. Steel on the tension reaches its yield strain of 0.0025 simultaneously. So these two strains are fixed for me, right? So if I connect these things, then you will find that my neutral axis depth is fixed. So this is my neutral axis depth, which is xu. So you can see here, this distance I know, which is 550 mm. So this is the level of steel is at a 550 mm from the topmost compression point. So this distance is known to me, right? So epsilon c is taking a value of 0.0035 and epsilon t is reaching yield value of 0.0025. So these two strains are fixed. And I also know what is the level of location of my steel. That means the effective depth for steel is known to me. So two strains are known. I know the distance this. So what is this distance? It's nothing but your d minus x. Okay. So d is basically 550 minus x. Okay. So using similar triangle or xu, because it's a ultimate condition, right? So using similar triangle, we can calculate that as 0.0035 by xu should be equal to 0.0025 by 550 minus xu. So if you solve for this, you will find xu is equal to 320.83 millimeter. Okay, so this is the neutral axis. So for a balanced condition, neutral axis depth is given because I am fixing the strain at the top compressive fiber strain, and I'm also fixing the strain at the tension strain. Okay, so neutral axis depth can be quickly calculated. Okay, now using that, neutral axis is known. Okay, now I can go back and calculate my equilibrium condition. So what should be my equilibrium condition? Concrete force in compression should be equal to tension force from steel. Okay. Now XU is known, right? So what is CC? We have done that calculation. CC is nothing but alpha 1 F prime C beta 1 XU times B. What is tension force? Now steel is reaching yielding. It has already reached yield strain of 0.0025. So TS is nothing but Fy multiplied by AST, right? So you can calculate this. What is alpha 1? In the previous calculations, if you look at it, for a strain value of 0.0035, we got alpha 1 equal to 0.81 and beta 1 equal to 0.90. Okay. So using this, if you substitute in CC, you will find that CC equal to 0.81 multiplied by, sorry, 0.81 multiplied by 40 multiplied by beta 1, which is 0.9, multiplied by XU, which we have calculated that to be 320.83, and breadth of the section is 400. Okay. So that should be equal to TS, which is basically TS, which is equal to yield stress. I know, but what I am interested is what is the amount of steel that will contribute to the, or that will lead to balanced condition. So AST is what I'm interested in finding. So 500 AST. So anyway, equilibrium condition has to be satisfied. So from this, I can calculate my AST to be, if you substitute this, basically 0.8140, 0.93, 20.83 multiplied by 400 divided by 500, you will end up with AST equal to 7480 millimeter square. Okay. So if in this section of 400 mm width and a depth of 600 mm, if I am providing a steel of 7480 mm square, that will lead to a balanced failure condition. So what is a balanced failure condition? Concrete at top reaches a strain of 0.0035. Steel on the tension side reaches a strain of 0.0025 simultaneously. Both of them will reach their value at the same time. So what is the percentage of steel that what we are calculating? So we calculated that as rho, which is nothing but AST by BH multiplied by 100. So if you do this numbers, you'll find that balanced reinforcement ratio is working out to be 3.12 percentage. Okay, this is your rho balanced. Okay, this is nothing but AST balanced. For this assumed stress strain curve, which is concrete parabolic curve, without any factors, partial safety factors, steel also I'm taking elastic perfective plastic. That is, for these kind of condition, this for this section, the balanced reinforcement ratio works out to be 3.12 percentage. Okay, so this is how we calculate your balanced condition. So for balanced condition, we know the strain at the compression fiber and steel. From this, neutral axis depth can be calculated. Once neutral axis depth is calculated, you can equate the CC to TS and find out what is the AST that will lead to balanced failure condition, right? So this is the way we calculate. Now for this section, let us calculate now how we can do this moment curvature analysis. I'm going to do only for one strain value, okay, and then see how do we take this. Now if I copy this, okay, substitute this here. Now only thing is this AST, I'm going to take this value as not this, okay, and this is not, okay. So this AST, I'm going to take this as equal to 7,000. How much we calculated? 7,480 millimeter square. Okay. So now for this, let us calculate what is the moment and curvature at ultimate condition. So now what is the ultimate condition? When the concrete reaches 0.0035, which is your actually balanced condition, right? So let's see. So strain profile, that what I'm going to take is 0.0035. This is, let's say, epsilon t, and this I'm taking it as 0.0035 at strain at the top. Okay, that is the first thing that we take. Okay, now I am going to take for this steel of 7480 mm square. What is the, as I'm going to assume a value of your XU, which is 320.8 mm. Okay, so what is that? We calculated that to be 320 points. So this is your failure condition. So that we have calculated that XU. Okay, and epsilon t also we found that it is equal to 0.0025. Now let us see what is that we are getting. See what we are getting out of it. Okay, so from strain distributions, again, if you calculate that, basically, if I assume strain distribution for this distance is again is going to be d minus x, okay, or which is xu, is 320.83. Okay, so from strain distributions, again, we can calculate that is 0.0035 by 320.83 should be equal to epsilon t divided by 550 minus 320.83. So if you do that, again, you will find epsilon t equal to 0.0025. That's what we did for balanced reinforcement ratio calculation. Now for this, I want to calculate moment and curvature for this strain distribution. So that is what I am trying to do. Okay. So what is tension force? Tension force, we know that it is okay. So tension force, we can calculate that as epsilon t. We have calculated epsilon t is 0.0025, which is equal to epsilon y. That means stress will be equal to Fy, which is 500 megapascal, right? So Fs multiplied by Ast, so which is nothing but 500 megapascal multiplied by what is Ast? 7480 mm square. So if you do that, how much you get? And if you divide that by 1000, you get it in kilonewton. That works out to be 3740 kilonewton. Okay, so this is kilonewton. So this is your tension force. Of course, we found our XU from neutral axis depth from your equilibrium condition. So obviously, when you back calculate your CC, which is basically we calculated again beta 1 equal to zero point 0.9 and alpha 1 equal to 0.81. So CC is nothing but alpha 1 F times C beta 1 XU multiplied by. So if you again substitute back for these values, you will find that nearly equal to same 307.42 kilonewton. So we can write that CC is nearly equal to that of tension. So equilibrium is achieved. Because this is balanced condition. Okay. Now what is that we are interested is in calculating the moment resistance, right? So let's go ahead and calculate the moment resistance. Now for this strain condition, and this is the strain condition. So what would be the stress distribution? Okay, stress distribution is going to be concrete. We are following now parabolic curve. So it is going to be low value and it's going to go up like this and it's going to go like this. Okay, so this is the stress distribution, right? From parabolic Hognestad model. Okay, so this is going to be some FC and your F prime C will be somewhere here. Okay, so when you integrate all of them, that is difficult. That is why what we have done, we have converted them into an equivalent rectangular block, which is equal to alpha 1 F prime C, and this is nothing but beta 1 multiplied by XU. So when you integrate all this force, okay, so that is basically going to give me CC. Okay, what is CC? That's what we have done. CC is nothing but alpha 1 F prime C beta 1 XU multiplied by B. Similarly, I'm going to have tension force here, which is TS, which is nothing but Fs multiplied by AS T here. Okay, so this is the AST. Right. So this is your force diagram. So what is the moment resistance that what we are going to get? Moment resistance is I am taking moment about any point. Either you can take moment about CC or about TS. So if I'm taking moment about CC, I'm going to get moment resistance will be equal to TS multiplied by this lever arm Z. So if you go back, my moment resistance. So what is lever arm? Lever arm is nothing but your effective depth D minus beta 1 XU by 2. Okay. So this is the distance. So this distance is your beta 1 XU by 2. Okay. So the lever arm is going to be D. This is your effective depth. Okay. So this is your effective depth, which is your 550, which is basically we can write lever arm as 550 minus, which is beta 1. Beta 1 value, how much that we have taken? 0.9 multiplied by XU is 320.83 by 2. This is your lever arm. So if you go back and substitute, what is your moment resistance? Moment resistance will be equal to tension force multiplied by the lever arm, which is we have calculated as D minus beta 1 X by 2. So if you substitute that, it is going to be 3740 kilonewton multiplied by 550 minus 0.9 times 320.83 by 2. So if you substitute that values, you get moment corresponding to that is going to be 1517 kilonewton meter. Okay. Now, what is the next? Curvature? Curvature, again, if you go back, what is curvature? Curvature is nothing but this is the slope, which is your phi. Now, what is phi here? Phi can be written as epsilon C u by xu, which is nothing but your xu, right? So, which is equal to 0.0035 by xu, which is 320.83, which works out to be 10.9 into 10 to the power of minus 6, 1 by millimeter. So you see here, the previous section, which had a very low reinforcement ratio of 1200 mm square, it had a curvature at failure of 68 into 10 to the power of minus 6. Now I have increased the steel from 1200 to 7480 millimeter square. Then the curvature at failure has reduced from 68 to 10.9. So what can we infer from here? If I put more and more amount of steel on the tension side, curvature at failure is going to reduce, though you are going to gain some moment resistance. So if you compare those previous cases, you will find that the moment resistance for the previous case, okay, if I have to compare these values, so we got a moment of 1517, and let's go back and compare. Okay, now when your steel, okay, let me write that as AST. Okay, maybe I'll put this black. When AST it was 1200 mm square, your moment resistance mu and curvature. Moment resistance was how much? We have calculated that to be 300 and if I go back and check the value, so we got about 316. Okay, so if you go back, so you get moment resistance of 316. This is in kilonewton meter. Okay, and curvature, let's say if I put it as 10 to the power of minus 6, 1 by millimeter as unit, for this section, I get 68.1. When AST became, this is basically what was the percentage of steel? It was only half a percentage. Okay, very low amount of steel. Now, when the AST has increased to 7,000, how much was it? 7,480. That corresponded to a ratio of 3.12 percentage. So, when the AST becomes 7,480 millimeter square, corresponding to a percentage of 3.12 percentage, Then your moment resistance, we have calculated that to be how much we got? 1517 kilonewton meter. 1517 kilonewton meter. Now, what is the curvature at failure? We calculated that to be how much? We calculated that to be 10.9, okay, into 10 to the power of minus 6. So you see here, the steel roughly I have increased from 1200 to 7480. So how much time that I have increased? 7480 divided by 1200 is roughly 6.2 times. Similarly, curvature also, if you see, it has reduced from 68.1 by 10.9. So you see, the more the amount of steel, and this is your balanced condition. Okay, that also you have to keep in mind. This is your balanced condition or balanced ratio. This ratio of steel is your balanced ratio. We will see that in the next parts. If you put steel more than the balanced ratio, you will not get much benefit in increase in moment capacity. At the same time, the curvature also will slightly reduce. So putting steel more than the balanced reinforcement ratio is not really going to be advantageous in a singly reinforced section. So that is what we are going to say. So with increase in steel, what we can say is the moment capacity is increasing, but however, the curvature is decreasing. Okay. So curvature is decreasing. So it has gone from 68 to 10.9. However, moment capacity is increased from 316 to 1570. It's not linear increase, but there is a proportional increase. I put more amount of steel, I also get nearly same proportion of moment resistance in capacity. So this is what we have to see. So if you do the same calculation, let's say we do it for one more condition. Okay. Okay, so now we are going to do for one more condition. Let me copy this. Okay, so let's do the calculation for this. Now, only thing is now I am increasing this to, okay, so this becomes now 9600 mm square. Okay, so I am bidding. First case was 1200, next case was 7480. Now I'm putting steel more than the balanced reinforcement ratio. Let us see now what happens. So this 9600 corresponds to 9600 divided by 400 multiplied by 600 into 100. If you do, it works out to be 4% of steel. So the steel, what we are putting is 4% of steel. It's quite a high amount of steel. Now let us see what happens for this condition. Okay. Now, what is the ultimate condition? Again, the same. Okay. So how do we define the ultimate condition? So you take this and you take this strain of 0.0035 in compression. That is what ultimate condition is. And steel, we don't know what is that tension steel. For balanced condition, we know, but this we don't know what is the condition. Okay, so we're going to write that as just epsilon t, and then I'm going to assume a value for my xu. Okay, so let's say I take a value of 344.25. Okay, so if you look at it, I'm assuming this xu. Of course, I have to make sure that for this xu, compression force is equal to tension force. So once I got my xu, then I can calculate my epsilon t. So how do we get your epsilon t? So from linear strain distribution for 0.0035 by 344.25 should be equal to epsilon t divided by this distance is d minus x, where x I have taken it as 344.25. So it is going to be 550 minus 344.25. So if you do that, you get my epsilon t equal to 0.00209, which is less than 0.0025. So this is what is the value? This is your epsilon y. So we can say that epsilon t is less than epsilon y. or when the concrete reaches its failure strain of 0.0035, steel in the tension has not reached its yielding value. So we have discussed in the previous part, we always, before concrete reaches its failure strain of 0.0035, we want steel to reach its yielding value. Then only it can stretch like a rubber band and it is going to give you a lot of warning. So if you put more amount of steel than the balanced amount of steel, you are going to limit the strain in the steel to be lesser than the yield value, which is not a good design. So we can calculate your forces. Okay. So again, from this, if you look at your concrete forces, okay, from equivalent rectangular stress block, so we can take this to be this alpha 1 F prime C. This is going to be beta 1 X. Okay, let's say XU. And your CC is nothing but alpha 1 F prime C beta 1 XU multiplied by B. Similarly, this is going to be your stress on the tension side. Let's say this is Fs. Now this tension force is Ts is going to be As multiplied by Fs. Okay. So if you substitute these values for this, let's calculate. Now what is that we're getting? So it is over reinforced. So tension force can be calculated as, now the strain in the steel has not reached yielding. It's still elastic, within the elastic limit. So stress is going to be 2 into 10 to the power 5, which is the elastic modulus, right? Multiplied by 0.00209 and multiplied by the area of steel, which is 9,600 divided by 1000 to get the force of kilonewton. If you do that, you get a force of 4012.8 kilonewton. Okay. Similarly, we can calculate your compression force as well. So what is the compression force that you'll get? You'll get a compression force for that. Again, for epsilon c equal to 0.0035, we know that alpha 1 is 0.81 and beta 1 is 0.90. So Cc can be calculated at 0.81 times 40 multiplied by 0.9 multiplied by XU, which is 344.25, multiplied by breadth, which is 400, and then the whole thing I divide by 1000 to get it in kilonewton. So you'll find that it is working out to be 4015 kilonewton. Okay. Again, we are structural engineers. For 4000 kilonewton, 3 kilonewton difference is okay. So we can say that Cc is nearly equal to Ts. So equilibrium condition is satisfied. Then I can go back and calculate my moment resistance, right? So you can get your moment resistance. So now how do we get your moment resistance? Moment resistance is again basically Ts multiplied by D minus beta 1 XU by 2. Okay. Now what is Ts? Is basically 4012.8 multiplied by D, which is 550, minus beta 1. Beta 1 is 0.9 times XU. What is XU that we got? 344.25 by 2. So if you substitute that, what is the value that you're going to get? So you get a moment resistance of, if you substitute these values, you get a moment resistance of, you get a value of M is equal to, let's say 4012.8 multiplied by 550 minus 0.9 times 344.25 divided by 2. So you get divided by again 1000. You get a moment resistance of 1585 kilonewton meter. And what will be the curvature? Again, epsilon Cu by Xu, which is 0.0035 by Xu, which is 344.25. That works out to be how much? 0.0035 divided by 344.25. So you get a curvature of about 10.1 into 10 to the power of minus 6 1 by millimeter. So again, we can compare, we can go back to this. Okay, now when the AST has become 4 percentage, which corresponds to 9600 mm square, which corresponds to 4 percentage. Now what is the moment resistance that we got? We got a moment resistance of 1585 and curvature of 10.1. So moment resistance 1585 and curvature of 10.1. So you see here again, if I put more steel than the balanced ratio, 7480 to 9600, the moment capacity has marginally increased, only marginally increased. If you look at it, 7500 and 9600, I have put almost 2100 mm square more than the balance condition. But however, the moment resistance what I am getting is only marginally has increased from 1517 to 1585 kilonewton meter, not much. But curvature is also reducing. So you can clearly see that by putting steel more than the balanced reinforcement ratio, you're not going to get much benefit in moment resistance. At the same time, curvature at failure is also going to reduce. In fact, if you have a large curvature at failure, it is a good design. That is what it is happening in this case, which is your under reinforced failure mode. So that is what we are interested in. Okay. So with this example, we have shown that this helps. Okay. So we were doing this problem with a very heavy reinforcement ratio of about 9600